All right, so today we're going to talk about shortest paths, and couple of, we'll at least start with one problem and then move on to a more general one if we have the time. So let's see what shortest path is all about. We're going to assume that we are given a graph, and all we want to do is to use this graph as a network and figure out the shortest paths from point A to point B. So you can imagine that you live in Miami, of course, and you want to know what's the shortest path to anywhere. Let's say to Kansas City, to Buffalo, New York, or wherever. And what you'd like to know is what is the route you should take, and in order to figure out this shortest path. And you want it to be precise. You want it to answer truthfully with the distances that are given to it. Of course, Google Maps seems to do this pretty easily, so it's unclear why this is useful, but it turns out that, give me a second, looks like, now it's sharing, everything is okay?
Yes, yes.
Okay. So Google Maps does this pretty easily, it seems, yet we do want to figure out, it's not just a matter of maps and distances. It turns out that this problem is of interest even in other settings. And we can talk about that in a different context. So if you work for American Airlines, these are problems that you'll be solving on a daily basis to figure out all sorts of things. So let's see how to make this problem more precise. The precise problem is something like this. You're given a graph, and the graph is shown here. In this case, this is shown as a directed graph, but it really doesn't have to be directed graph. It could be an undirected graph. And this graph can be written as an adjacency list structure, like so. The only difference is that not only is the graph directed, it's also a weighted graph. So every edge has a weight associated with it. So this edge is a weight 10, this edge is a weight 19, and so on and so forth. We can also represent the adjacency list in this form, which is a slightly different format. It's simply the list of edges that are present in the graph. So there's an edge from D to C of weight 10. That's this guy here. There's an edge from A to B of weight 12, edge from D to B of weight 23, and so on and so forth. And over here, there's a dictionary. What do you think this dictionary does? Yeah, give it a shot. What is the role of a dictionary?
The dictionary basically stores like key value pairs.
That's right. Yeah. So over here, there are two things given. There's one of these is a key, and the other is a value. That's what we're going to assume.
Right.
So let's assume that this is the key and this is the value.
Oh,
so
sorry.
Go ahead.
No, I might be wrong here, but this is okay. So this is storing like the key is the key is the node, and then the value is its previous. for each one of
What
them.
does previous mean? Previous should be another, you mean another node, or what does that mean? Anyone else? What do you think this dictionary does? So dictionary is a map, or as you said, it's a key value pair. If the key is A, B, C, D, E, and if the value is 0 or 1 or 2 or 3 or 4, what do you think it does? So what it's doing is it's taking this graph, the vertices of this graph, and it's mapping it to an index. As you can see, each one has a different index, 0, 1, 2, 3, 4. That's the index in the adjacency list. So if you are interested in all the edges that are going out of vertex D, you would first go to the dictionary. That'll tell you that it has index 0. You would go to position 0, and it'll tell you all the edges that it has. So it has an edge going to 3, and it has an edge going to 1. That would be B and C according to this. From D, you have edges going to B and C. Is that clear? So the dictionary is a convenience that you can use to implement graphs using adjacency lists. You could also have had a dictionary that maps edges from here to this data structure. Remember, each row here is an edge. And if you give those numbers as 0, 1, 2, 3, 4, 5, 6, then you could map each of these edges to a row over here or to an entry in this data structure. For that, you would need a different dictionary. So these are all just ways of implementing things. All right, so that's just to tell you, this is from a different book. This is from Weiss's book on data structures. This is the data structure that he gives for graphs, but it's always useful to know these variant data structures and then see what you want to do with it. Okay, so let's assume that we are given this graph, and we're going to pick a vertex. It doesn't matter which vertex. And we're going to see the shortest path from that vertex to every other vertex. In this case, let's say we want to look at vertex A. We would like to figure out the shortest path from A to every other vertex. And you see this comment here that says the shortest path from A to C. There is clearly no direct edge for this. And it turns out the shortest path is going all the way around like so. Because if you went this way, it's going to be of length 12 plus 11, 23 plus 43, 66 plus 10, 76, which is shorter than any other way to get from A to C. So this is an example of a shortest path problem that we'd like to solve. So next I'm going to show you, I'm going to run an example of shortest path problem. But first we're going to do a simple case, and then we'll do a more general case. So what's the simple case? The simple case that we're going to look at is an example of an unweighted shortest path problem. Unweighted shortest path means that every edge in this graph, it's directed, but it's not weighted, meaning, or you can also think of it as all the edges have the same weight, let's say weight 1. And we want to figure out what is the shortest path from this vertex V2 to everywhere else. Okay, and we would have to do this computation on the graph that's given here, and it works in stages. And I'm going to show you how this proceeds for the actual algorithm. Any questions so far?
You could use a 2D matrix to store distances too, no?
You could, but as it turns out, a 2D matrix has a has a space complexity and time complexity of n squared. And so all algorithms that you use are going to take time n squared, regardless of how many edges there are. But what I'm going to show you now is a simpler way to do it that doesn't require n squared time complexity.
Right.
So, so the way this works is very simple. You start from here and you essentially do breadth first search. And so breadth first search will say, since you're starting here, you look at both edges going out and you label them as 1. Then you look at all the edges going out of vertices labeled 1. In this case, there's only there are these 2 vertices that go out, and both of these get labeled 2 because they lead out of 1. There are no edges going out of here, so that's the end of that story. Then you look at both vertices labeled 2, and you look at all the edges going out, and both of these will get labeled 3, and that's the last of the steps here. So these 2 become 3, and you would have traversed the whole graph. So essentially, it's doing breadth first search. There's nothing different about it, and it turns out to be enough. And you already know that breadth first search runs in linear time, and therefore is faster than your n squared algorithms. So this looked very trivial, and the reason it's trivial is because, of course, because this is an unweighted graph. Now, there's an alternative way to think about this whole problem, and that's what I'm going to tell you next. Are there any questions about what you've seen so far? Okay. So far what you've seen is very trivial, very simple, and you're going, so what's new here? So I'm going to show you a different way to think about shortest path computations. And here's how this works. So let's go back to where we started. We started with Vertex, with this Vertex 2, V2, and we wanted to do shortest path to all the vertices in the graph. That's why it's called a single source shortest path problem. So a different way to think about this is think of this as think of this as some physical network, and think of pouring a little fluid into this network right here at this vertex. If you start to if you start to pour, let's say you pour some oil into this. Think of this as a little hole there, and you're pouring a fluid into it. Now, also imagine that these edges here are unidirectional pipes that will take your fluid away as soon as you pour them. So in this case, what will happen is if you were to pour some fluid over here, it'll immediately start to flow in both these directions because both these edges are leading out. So imagine that both these edges are flowing at the same speed. And because both of these edges are of weight 1, what you'll see is that after some amount of time, the oil would have flowed from here to here and here to here at exactly the same time because they were both at distance 1. So if you think about the speed, let's say the speed is 1 unit per second. In that case, when you pour oil in here, in roughly 1 second, you would have oil reach V0 and V5. Now, if you wait a little bit longer, there are more edges going out of these vertices, and so the oil will start to flow further out from here. And imagine that you can pour as much oil as is needed at this point. So oil will go off and reach both these vertices at time instance 1. And then at time instance 2, you will have both these vertices become the oil would have reached those 2 vertices by time instance 2. And then in time instance 3, you will have oil reach both of these vertices. So you will know exactly at what time the oil or the fluid will reach each of the vertices. And that's exactly the numbers that you see here. This guy is where we started. So the oil was there at time instant 0. Then these two were where the oil reached at time instant 1. These two were reached at time instant 2, and these two were reached at time instant 3. So by imagining it this way, it turns out that it's you can visualize the Dijkstra's shortest path computation, or you can also visualize breadth first search in this case. Now, the reason to think about this in this manner is because we're going to apply the same idea to a weighted graph. So far, we've only looked at unweighted graphs. So the question is, what happens when you start to look at weighted graphs? Looks like Patrick is here. That's good. What happened to David? Looks like he dropped off hard. Maybe his connection died.
Yeah, he's been joining and leaving, so I think it's the connection.
Okay. All right. So let's continue with what we were saying. There's a message here. Patrick also has to leave. Okay. All right, no problem. Okay, David is back. All right, so now let's use the same analogy, but for a weighted graph and see what happens. Here's an example of a, well, actually, this is just showing you the same one, but with unweighted graph, I think. So at time instant 0, V2 has you can think of it as getting lighted up. At time instance 1, the fluid would have reached V0 and that would light up. And at time instance 2, these two would have been reached and they would get lighted up. And at time instance 3, these two would have been reached. So now the question is, how do we generalize this to an arbitrary weighted graph? And it turns out the exact same analogy works out really well. Well, I'm going to come back to this a little bit later, so let's just bear with me. What I want to do is to show you breadth first search and convince you that a few minutes later that Dijkstra's algorithm turns out to be exactly same as breadth first search, but with a few modifications. So you can, and I mentioned this before, that you can implement breadth first search using a queue. So the way this algorithm works is to initialize a queue, and you're given a start vertex. So in the at first, all you do is to you initialize the vertices, and then put just one vertex on the queue, and that's the start vertex. And then there is a simple while loop, which does the following. Every time you pick one vertex from the queue, look at all its neighbors, and put all the new ones onto the queue and label them appropriately, which is exactly what we did in the example that I showed you. And it turns out that this takes care of breadth first search. If you recall, breadth first search does essentially this. You start with one vertex, look at all its neighbors, then you look at the neighbors' neighbors, and one way to look at all the neighbors' neighbors is to put all of these onto a queue and process them one by one and look at each of their neighbors. And if you keep doing this, it turns out that you achieve breadth first search, and that's what this algorithm is showing you. And the time complexity here is just n plus m. And you see here that there are two commands, there are 3 or 4 commands on the queue. You initialize the queue here. You put one node onto the queue, and this says, while this queue is not empty, remove whatever is at the front of the queue and look at all its neighbors. If that neighbor has not been processed, put it on the queue, put it at the end of the queue. And you keep doing this until your queue becomes empty. And at the end of this, you're guaranteed that you would have done essentially a search process by visiting every vertex and every edge in the graph. And this order is called the breadth first search order. So I'm going to now show you how this smoothly generalizes to the general or the weighted case for you to understand. There are a couple more messages here. Let me just quickly look at that. Okay, no problem. Yeah. Okay, so let's continue here. I'm going to come back to this here and show you. First, I'm going to show you an example of doing shortest path algorithm on a general weighted graph, and then tell you how this can be implemented using Dijkstra's algorithm, which is basically a generalization of the breadth first search that you saw earlier. So we're going to use the same analogy that we had before. And what you'll see is that if you start with, oh, sorry, in this case, it seems that you're starting with V0, not with V2. So let's see how that goes. So if you start at V0, that's going to be reachable by the fluid at time 0. So you're pouring fluid down this vertex V0, and what will happen? At time 1 and at time 2, the fluid would have reached V3 first and then V1 later on. So at time instance 1, the fluid would reach V3 for sure. At time instance 2, the fluid would reach V1. Now, the question is what happens next? In order to figure out what happens next, you figure out which one gets the fluid reaches there first. And then from there, you look at all the edges going out. In this case, there is 2 and 4 and 8, and also this 2. And you can label all those guys with an appropriate label. So since V3 will be reached at time instance 1, the fluid will then continue from there, and you will see that this will be reached at 3, this will be reached at 5, this will be reached at 9, and this will be reached at 3. Now, the numbers that you get on the vertices are not final, and that's because they are still on the queue, and it's possible that there are alternative paths that might end up being better or faster or shorter. So we're going to continue this process, and you'll see that eventually things the process would have figured out the shortest path to everything over here. Now, so the first time around between these two vertices, this is the one, sorry, you're starting here. The first time around, the closest vertex is V3, and so that's where the fluid is going to reach first. In the next, the next thing that you're going to reach, of course, is V1, and that's because this is reached at 2, this is reached at 3, this is reached at 3, and these are reached much later. So therefore, this is going to be the next vertex that's going to be reached by the algorithm. So this guy gets labeled as 1, this guy gets labeled as 2. If you continue this process from 2, you see that this can be reached at time instance 3, but that one comes from here. So can this, so both of these get reached at time instance 3. And once they are processed, you're now ready to process these guys. If you came from here, you would know that you can reach here in 3 plus 6, that's 9, at time instant 9. You can reach this guy at time instance 1, and so this can be reached at time instant 1 plus 4, that's 5. And this guy here can be reached at 3 plus 5, that's 8, or 1 plus 8, that's 9. Later, when you figure out that this guy can be reached at 5, and you see this edge of length 1, and you process this at the end, you'll see that this can be reached at time instant 6. So essentially, you can reach, if you start from here, you can reach this guy at time instant 1, this guy at time instant 2, these two at 3, this one at 5, and this one at 6, just based on the edges that you processed. And you're going to process the vertices in a specific order. In this case, it's the order is going to be the increasing distance from the start vertex. Does that make sense so far? Everything okay with this? Any questions?
Yeah.
Okay.
Uh, This is just something that it looks to me. I don't know if I'm seeing it or if I can say this correctly, but it kind of looks like a minimum spanning tree, but with breadth first search instead of depth first search.
Yeah, you're right that in the end you get a spanning tree, but it's not a minimum spanning tree, and we can talk about that later.
Oh, okay, okay.
It is a spanning tree because you are reaching all the vertices. In the end, it is going to do some kind of a search. The order is not breadth first search because the edges are weighted, and that determines what order you're going to visit the things. And finally, what you get is not a minimum spanning tree for a variety of reasons, and I'll show you that later. All right. So here is the algorithm that we just implemented. And it turns out that the only difference we're going to make here, if you remember the breadth first search that I showed you, it's almost exactly the same code, except that instead of a queue, I replace it with a priority queue. Now, what does that mean? So if you recall, let's go back here for a second. Yeah, so here we used a queue, and because it was a queue, when you visit a vertex, all its neighbors will get visited in a specific order because they're all at the same distance. And then those guys' neighbors will get visited after you visited all the first order neighbors. You're then going to go there, and they also are going to get visited in a very specific order. So that's what breadth first search does. And because all the edges are unweighted, they are equivalent to having all edges being of length 1. And so therefore you can predict exactly in what order they're going to get visited. And that's the ordering of breadth first search. In Dijkstra's, instead of a queue, we are using a priority queue. And the priority value that we're going to use is the distance from the source vertex. And remember, in this case, the source vertex is this vertex S from which you started the whole process. So what happens, let me go back here. You'll see that the order in which the vertices get processed, if you allow the priority queue to process it, it'll process this first, then this, then this, then the two vertices labeled 3, then the vertex labeled 5, and then the vertex labeled 6. That's the order in which it would process all the vertices, and that's because it's a priority queue. So also another way to think about the numbers that we have associated with every vertex is this is the time instance when the fluid, once it's poured in vertex 0, that's the time instant when it'll reach the other vertices. So in time instant 1, it'll get here, time instant 2, it'll get here, time instance 3, it'll get both these places, then here it'll get at time instance 5, and here it'll get in time instance 6. So another way to think about this is that it's the length of the shortest path from the source vertex, from the start vertex. So this guy is at distance 1 from here, this guy is at distance 2 from here, this guy is at distance 3 from here, and that's because you have a path 1 plus 2. This guy is at distance 5 because you have a path 1 plus 4. This guy is at distance 6, and why is that?
Wait, go ahead, Clement.
how do you get from vertex V0 to V5 in distance 6?
Oh, you go from
V0
go to V3 and then to V6.
and then to V5, right?
Oh, 5, sorry.
So if you go this way, then it's shorter than going from here to here, because that would be 1 plus 8,
Mhm.
or 1 plus 2 plus 5, or 1 plus 2 plus 6 plus 1. All of these are longer. So the shortest path from here to here turns out to be V0, V3, V6, and V5. Is that clear?
Yes.
And the nice thing is that the priority queue will process them in that order. It will definitely process V6 before V5. It'll definitely process V3 before V6. It'll process V3 before V4 and V2, and so on and so forth. And that's all because you used a priority queue instead of a queue. If you had used a queue, then it's going to be essentially the first in, first out order, and you don't have much control over how they're processed. So this leaves us to try and understand why is a priority queue so important when you apply Dijkstra's algorithm. And that's what we're going to try and understand next. Any questions so far? Okay. If you don't, go ahead, Clement.
I guess my question here would be like, say if we wanted to have like the exact path, like if we wanted to actually have the path.
Yeah, we'll worry about that in a few minutes. So let's focus first on the distance. That's a great question, but bear with me. I will get there.
All right.
Okay. Now, what I want you to focus on is, why do I need a priority queue? Okay. What's sacred about priority queue? If I'd replace that with a queue, would it still have worked?
No.
No.
Why not?
Because with the
I mean, I still have the edge weights. It's not like I'm going to ignore it. So you know, I process this, and I'll sorry, I'm starting from here. I'll process this, and I know I can get here in at time instance 1 and 2, so distance 1 and 2, and eventually I'll get from here to here. So I would compare these two, and I'll know that this is better. So I would have 1 plus 2, that's 3. I'll have 1 plus 4, that's 5, and so on and so forth. So what's wrong with this?
The nodes you see will depend on whether added to the queue. Or with a priority queue, you can ensure that starting from one node, you will first visit its adjacent node with the lowest edge weight.
Why should I do that? Why do I care?
Because we want the shortest path.
Yeah, but what if I had processed V5 first? Anything wrong with it? I mean, I would eventually get to, sorry, again, I keep going from here. I have to go from here. What if I processed V1 first? How would it have messed me up?
Okay, so if you were to process, if you were gone from V0 to V1, then at V1, you could have gone to V3, and it would have had a time visited of 3. Yeah, 2 plus, oh no, sorry, 5, 2 plus 3.
Yeah.
But that's incorrect, because you could have gone from V0 to V3, and then V3 would have a time scene of just 1.
Well, you know that both of these are adjacent, and so they will get processed as coming from these edges, and so this would still get 2 and 1. Would there be a problem here if I process this first?
I'm gonna try. So basically, I mean, what I'm thinking is, how do I say it? We're basically not guaranteed anymore that, like, we're dealing with the shortest path up to that point.
Yeah.
When we're dealing with the when we're dealing with the nodes, because
Right.
because
Okay.
yeah.
Good. Yeah. So your answer is correct. What we are going to do is to try and understand why that's correct, because the intuition behind that is not so easy to prove. Okay, so let's try and figure out why this is happening. So much of this comes from the following figure. This figure says that if the shortest path from S to W, so imagine that I want to find the shortest path from S to W. And also imagine that the shortest path does go through this vertex V. So my shortest path from S to W goes through vertex V and then uses the edge from V to W. So if this were true, then what I'm going to tell you is that this squiggly thing must be the shortest path from S to V. And I'm going to ask you why that would be true. Should I repeat it?
Yes.
Please.
So imagine that my shortest path from S to W, so imagine that this is Miami, imagine that this is Atlanta, and this says that my shortest path from Miami to Atlanta goes through, I don't know, what is that town before that? Let's say Macon, Georgia.
Orlando, maybe?
Orlando would be okay, but it's not close enough. So let me say put something closer to Atlanta. I think there's Athens,
Jacksonville,
Georgia, okay,
Gainesville.
Jacksonville. Fine, Gainesville sounds good. Yeah, Gainesville. So let me mute one of you. There's some noise there. Okay, so let's assume that my shortest path from Miami to Atlanta goes through, what did you say, Gainesville. What I'm going to tell you is that if that shortest path goes through Gainesville, then if I just stop at Gainesville, then the path I just took must be the shortest path from Miami to Gainesville.
Yes.
Why is that?
Because at least from this diagram, there's only one edge from Gainesville to Atlanta.
Right, but now I'm talking about Miami to Gainesville. Now, let me repeat this one more time. Let's say that I have some shortest path from Miami to Atlanta, and it goes through Gainesville. Okay, and I know this is the best path. It's the shortest, fastest, whatever it is that you want to think of. Now, if I were to take that path, and instead of going all the way to Atlanta, if I stopped at Gainesville, I can be guaranteed that I took the shortest path from Miami to Gainesville, even though I did not plan for it. Why is that?
Because you're taking the same path, except you're like stopping one edge sooner, basically.
Sure, but how do we know that there's not some other path that's better for Gainesville?
Well, I mean, when we're well, wait, are we already assuming that from the source to Atlanta, well, from Miami to Atlanta is the shortest path, right?
Yeah, that's right.
Okay.
I can guarantee you that my shortest path from Miami to Atlanta goes to Gainesville. Let's say I tell you this.
And
now I'm taking that shortest path to Atlanta, but I stop instead at Gainesville. And now I'm going to declare to you that, hey, I know for sure I took the shortest path to Gainesville.
Well,
am I speaking the truth?
Yes, because to say
Why?
that this is to say that this is the shortest path from Miami to say that the shortest path from Miami to Atlanta is through Gainesville is saying that you have the shortest path from Miami to Gainesville plus the edge between Gainesville to Atlanta.
Why are you assuming that?
Why?
Uh-huh.
Well, because okay. How do I put this? Okay. So when we
try proving by contradiction.
Okay. So
What does that mean?
basically proving that the opposite would be wrong.
Okay, go for it.
So like saying that.
So in order to prove by contradiction, what is it that you have to assume?
We have to assume that
whatever we wanted to prove is wrong.
Yes. Yeah.
And what is it that we want to prove?
We want to prove that the shortest path from
the path we took from Miami to Gainesville was the shortest possible path.
Yes.
Right?
Yeah, right.
So let's assume it's not the shortest path, that there is some other path that's shorter.
Yes.
So what's wrong?
If there were a shorter path from Miami to Gainesville.
So I'm going to draw that for you. Yeah.
If there was a shorter path from Miami to Gainesville, there would be a shorter path to Atlanta.
Very good. Yeah. That's what you want. So that's where the contradiction is, right? Okay. So let's try and draw this. So you understood what I was saying. So if there were a shorter path, oops, come on. Why is this thing not working?
So
it refuses to work. I have no idea why this.
It's all right. We can use our imagination.
Yeah, you just have to use it. So imagine that there is a shorter path from Miami to Gainesville. If that existed, then thank you. Then I could have now done an even shorter path to Atlanta, because I could take that green path to Gainesville and then use the same old edge from before. And that would be shorter than the first one that I claimed was the shortest path to Atlanta. So therefore, my first claim saying that my shortest path to Atlanta goes through Gainesville can't be true. Okay, so that's where the contradiction is. Is that clear?
That's clear.
Okay, so therefore, what it's really saying is if there is a shortest path from Miami to Atlanta, you can take any city along the way. It could be Orlando, Gainesville, Macon, whatever comes along the way. The path from Miami to that city must be the shortest path to that city. Because if there were a shorter path, I would have replaced that part of the path with a shorter one. Is that clear?
That's clear.
So therefore, if you take any piece of a shortest path, it's also a shortest path for some pair of vertices. Should I repeat that?
So what you're saying is like you can generalize and keep going one back, and
that's right. So it's saying that any piece of a shortest path is also a shortest path for some other pair of vertices. That's the magical part. So this is called the substructure property or optimal substructure property. So it must be composed of a bunch of other shortest paths. So if my shortest path from Miami to Atlanta goes through Orlando, if I know for sure it goes through Orlando, then the two pieces, the shortest path from Miami to Orlando and the shortest path from Orlando to Atlanta, it's enough to put them together and you would have the shortest path from Miami to Atlanta. Okay, so as long as you know that the path goes through Orlando, you can do this. So therefore, you take any shortest path and you take any of the vertices along the way, then your path includes shortest path from Miami to that vertex. Okay, that's what this says. So it might look a little trivial, but this turns out to be the key property for a bunch of other things to happen. And that's what I'm going to try to explain next. Any questions so far? Okay, so part of the magic happens here. This is what we said. In fact, this is what I said earlier. Imagine that this is Miami. Imagine that this is Atlanta. And it goes through, let's say the shortest path goes through Gainesville. Now, it's possible that you might find a shorter path later on. So assume that this path here is, assume that you found this path first and you thought that the shortest path to vertex W was 8. However, it's possible that later on you'll find something that's shorter. If you do that, then you would have to update this information. But if you were to do it in the order of increasing distance, then this problem would never occur for you. And that's why Dijkstra's algorithm uses the priority queue in order to make things happen. So at every instance of time, you find all the vertices that can be reached with a certain distance. And you take care of them, and then you keep going outward from that vertex. So over here, let's see, the next slide is more meaningful. Here is the start vertex. Think of this as Miami. Think of these as all vertices that can be reached with a certain distance or within a certain distance. And now you want to go a little further. So there is a vertex U that can be reached in DU. There's also a vertex V that can be reached in DV. It's better to process this guy if it is smaller than that guy, because then that might allow you to find a shorter path to this vertex later on. If you were to process this first, then you would miss the fact that there is a better path through something else. However, if this is the smallest, this is the closest vertex in S, other than the ones that are shaded here, then of course this would be the shortest one. It won't be U, and this guy would jump out of the priority queue earlier, and you would process this vertex first. So it turns out that because of the priority queue, Dijkstra's algorithm can be proved to be working correctly. And that's what we ended up using in our algorithm. And that's what the pseudocode here also uses. So all I did was, instead of the queue, I replaced it with a priority queue. Everything else turns out to be almost exactly the same, except for something over here. And let me explain this part by first going back to the breadth first search, so that you understand what we did there. So if you think about it, this is breadth first search. I started with a queue. I initially put only the start vertex, and then in every iteration, I pull out one vertex from the queue and put all its neighbors at the back of the queue. And for each vertex that I put at the back of the queue, I label it as to be of distance one more than the vertex V that I pulled out of the queue. So to start with, I pulled out the vertex S, which has the number 0. Then I put onto the queue everything that S is adjacent to, and I label them 1. One by one, I pull out all the vertices that are labeled 1, and I put onto the queue all the vertices that are labeled 2. Then once I finish with all the vertices labeled 1, I start with the vertices labeled 2, and then their neighbors will get labeled as 3, and then the neighbors of 3 would get labeled as 4, and so on and so forth. That's what we did with breadth first search, or essentially with Dijkstra's when we applied to unweighted graphs. When we applied to weighted graphs, the difference is slightly, the statement is slightly different. We update the distance to be W of distance is equal to V of distance plus the weight of the edge. So we look at the last edge, the weight of the last edge that reaches from V to W. If this final weight is less than what we had before, then we update it. Otherwise, we leave it as it is. But each time around, we change the value of the edge weight, and then we move forward. Now, what happens is that when you process new vertices, they may have other edges to things that are already on the priority queue. And so the priority value of the things on the priority queue might change. And that's what this particular command is over here. This is a critical one that changes the time complexity of the algorithm. And so it's worthwhile to try and understand that well. I am happy to answer some questions because I know this code, even though it looks suspiciously easy, it's actually quite challenging to understand this very, very well. So let me stop here for questions before I move on.
Quick question, question, I guess. So, I guess, in the algorithm, right? So, let's say, okay, so we're adding in the edges. I mean, we're adding the nodes into the priority queue, right? And
yeah.
let's say we went back to a node that was processed during an earlier decision.
Okay.
Do we?
Yeah.
Okay, so I guess my question is, how do we go about not going further with those nodes, because we already know they're not going to provide us a future shortest path?
Right. Okay. Good. So let's see if we can figure this out. Give me a second. Yeah, for that we need this picture here. So we are assuming, so this is one of the nice properties of Dijkstra's. Once it pulls out a vertex from the priority queue, it's never going to look at it again. And it would have assigned it the distance from the source vertex, and that number is going to be a final number. It's never going to change again. So here we're assuming that all these vertices in this gray area have been already pulled out of the priority queue, and they've been labeled, and you're never going to look at them again. At the time that it got out, that it was pulled out of the queue, priority queue, you looked at all the edges going out, and you labeled the vertices that are outside the queue and that have never been visited before. So at any given time, you are going to have on the priority queue a bunch of vertices that can be reached from here, but that have not yet been processed. But you only have tentative distances for them. You don't have final distances from them because they have not yet been pulled out of the priority queue. At the time that it gets pulled out of the priority queue, it's the nearest vertex to the source among the vertices that are not yet already been processed. So among all these vertices, the one that gets pulled out of the priority queue is closest to S. And so therefore, that guy gets labeled. And that also means that you cannot find a better path that goes through some other vertex and comes back here. So every time when you pull out something from the priority queue, you can be sure that you will never find a better path later on. And therefore, Dijkstra's algorithm works correctly because at that time when it comes out of the priority queue, its value is final, and we know that according to the algorithm, it'll never change again. And so that's what you see even in the code. And let me show you this one more time. So when you pull the vertex V out of the queue, you know for sure its distance is the closest to the source S among all the vertices that have not yet been processed. And at that point, you look at all its neighbors and you process them and assign them distances, but these are tentative distances, and you put it on the priority queue. If it comes out next, that's the one with the lowest value among all the distances from the source. So the priority queue has as its priority value the distance from the source, not the distance from somewhere else. So we always use as priority the distance from the source, and therefore when it pulls something out, it's the closest among the things that have not been processed. And that's why the whole thing works. So I can also show you the following here. This says, in order to understand Dijkstra's algorithm, it's important to understand that the array D is going to contain the length of the shortest path from the source S to the vertex V, and the priority queue is always going to be with priority value equal to the D value of that vertex. And that's why the whole thing works. Any questions?
No, that all made sense.
Okay. So there's a
Good.
little bit more. Yeah, go ahead.
No, I'm good. I
Okay.
understand.
All right. So there is one other little detail here, and that has to do with a function called relax. If you read the textbooks on Dijkstra, they will explain to you a function called the relax function. The relax function says if the distance to vertex V is smaller than the distance to vertex U plus the weight of the edge from U to V, then it means that the information you have currently is better than anything you have so far, and you wait, what did I say here? Yeah. So if the distance is already better than what you're trying to show, then you don't have to change, and so you leave it as it is. But if it is, then you go and fix it. But in the end, what you get is the shortest path to every vertex. So that's really what it's trying to say. I'm not sure what I had in mind when I said items and G. I made these slides a long time ago, so I'm going to leave that as it is. Another important thing to know is that when you pull out a vertex U from the priority queue, you process all its edges and you write down their distances and put it on the priority queue. So over here, if oh, here I was trying to solve some other problem, and that's why I have all these strange things. We won't get into that for now. Let me just see if you understood what I was trying to say here in terms of the distance and the relax function. If there are no questions, then I can move a little bit forward. Now, it's important to really understand this if statement here. So think of what we have done so far. We started with the vertex S. That's our source vertex. That's the first vertex that we start with. And that has a distance of 0. So that's what it says here. S dot distance is 0. So the distance from the source to itself is 0. No big deal. Then we put every vertex onto the priority queue. And for now, we know nothing about its distance from the source. So we're going to just label its distance as infinity, which means that it's going to be very large and it's not going to come out of the priority queue anytime soon. Now, we insert the vertex S onto the queue, and as long as the queue is not empty, the first thing we do within this while loop is to delete the smallest value from the priority queue. And of course, the first time around, the item that's going to come out of the queue is vertex S, because it has a distance of 0, and all other vertices have a distance of infinity. So 0 is smaller than infinity. So when you pull out something from the priority queue, out comes vertex S. And then for each vertex that's adjacent to vertex W from V, and remember the first time around vertex V is the same as vertex S, we're going to process all those vertices W and put that onto the queue. Before we put it on the queue, we're going to check whether, first of all, maybe it's not, maybe the new distance is better than the old distance. Remember, the old distance is just going to be infinity, so it's possible that the new distance is slightly better. The new distance, remember, is the distance to vertex. I made a mistake here. Oh, no, it's fine. If the current information on the shortest path from the source to W is larger than the new information of the shortest path to W, then that's what we're going to use. And what's the new distance? The new distance says because there's an edge from V to W, it's the distance to V plus the weight of the edge VW. And if that information is smaller than what we had before, we're just going to update the distance of W to be this new value. And we're going to adjust the priority queue appropriately because now we have a vertex whose priority value has changed. So that's really what happens with the priority queue here. We do one extra thing, and that is we always keep track of the parent of every vertex. Remember, the parent is the vertex that's the last vertex on the shortest path. So if there is a shortest path from source to W, then this says that the previous vertex on that shortest path is V, and that's because we use the edge VW in order to figure out a new shortest path. So the previous pointer will always give you the last vertex on the shortest path from source to that vertex. And that's all you need to know. Once you have this previous pointer, it's essentially what you get is a tree, and this tree is called the shortest path tree. And we can go back to this example and figure out what that shortest path tree is going to look like. And maybe one of you can use your markers to do this. Remember, the first thing that was processed was, of course, the source here. The first edge that was processed was this one. So this guy's parent is V0. Same is true of this guy. Its parent is V0. Now, the parent of both V2 and V4 is not V0, but it's V3. And the parent of V6 is also V3, but the parent of V5 is V6. And that's because the shortest path from V0 to V5 goes like this, right? It goes V0, V3, V6, and then V5. And therefore, its pointer is its parent is V6. So all that information is stored away, tucked away in by this algorithm in the right places in the right data structure. And so it has an amazing amount of valuable information that helps you to figure out the actual shortest path that Clement was asking about earlier. So if you follow the previous pointers, you will figure out the shortest path from the source to that vertex. And that's all you need to know here, and the algorithm works perfectly. Any questions?
None here. That cleared up everything for me.
Okay, so it turns out that the time complexity of this algorithm is n log n plus m plus n log n, and let's see how that works out. The first step is to build a priority queue. To build a priority queue with n vertices takes you n log n time. That's your first thing. Then we do a bunch of things here, and we then pull out from the priority queue one vertex at a time. In every while loop iteration, you pull out one vertex, and for each vertex, you process all its edges. Because we process all its edges, the time complexity for this part of the algorithm is going to be m. So you got n log n from here, m from here, and then this update priority queue could happen once for every edge in the graph. And because the update priority only takes log n time, this step could take you m log n time. And so therefore, of the three items here, this is the most expensive. And so the time complexity of Dijkstra is m log n. It turns out you can, by using some tricks, you can improve on this. By using a fancier priority queue here, you can improve on the time complexity, and you can make it m plus n log n. But for now, let's not worry about that. So if there are any other questions, I'm happy to answer them. So it's important to see here. Yeah, a couple of things that you need to know is that Dijkstra's will not work, it's not guaranteed to work if you have negative weight edges. And it gets even worse if you have a negative cost cycle. If that happens, then you have to use a different algorithm. You have to use Bellman-Ford and something else, and we'll talk about that next time. So Dijkstra's algorithm assumes that you have all positive or non-negative weights. And it's useful for you to look at this time complexity to do unweighted Dijkstra. It can be done in order like breadth first search, it can be done in linear time. That's order m. If you have weighted but you have no negative edges, then it's m log n. If you have negative edges, then it becomes m times n. And if it's even worse, if you have an acyclic one, again, you can do it very, very efficiently, and that's called topological sort. But you've seen that before, so I won't get into it. So this is what you need to know about the time complexity. This is the most important one that you need to know, Dijkstra's. And occasionally you might need Bellman-Ford. I can show you that some other time. Are there any questions? If you don't have any questions, then I am going to stop here today. And we will continue next week. And I can give you a mock competition problem, 1 or 2 problems on Dijkstra's for this Saturday.
Sounds good. Sounds good.
Sounds good.
Awesome.